Okay, woo, boy, do we have some stuff for you. All right, let's start with the equation for the force for the magnetic field, right? QV cross B, right? And I wrote as an integral here. To do that, I'm going to make my charges really small. I'm going to add each of them up, right, to get the total force, right? And so to do that, I'm going to have to do an integral, right? The V is dl over dt, right? That's the velocity. Now I do a switcheroo, right? I take my dq and I take my dl and I switch them really fast, right? So I get dl times dq over dt, right, cross B. But what the crap? dq over dt is just the current, right? So I get the current cross B times dl, right? And so now a little trickery here, right? Because the current is actually moving along the path dl, so there's not universal agreement as to whether or not the I should have the vector or the L should have the vector. It doesn't matter in any case that I've ever seen. It's your choice. And I'd like to say that I'm really consistent and I always do the same thing, but I don't. I just kind of know that they're the same thing, and I just do whatever feels more comfortable at the time. All right, there are two more substances or quantities that I need to know before I really dive into magnetic fields, right? I got to know about the current density, and we're going to give that the symbol J, right? And then we're going to talk about the surface current density. All right, so J is equal to rho times the velocity, right? Where rho is the charge density, right? So the way I like to think of J is imagine having a wire made up of a whole bunch of little tiny strings that are infinitesimally small. Each string has a charge per area, where that's the front face of the tiny string, right? And so in order to get the total current, I've got to add up the amount of current, or the J, in each little strand, right? And add them up over the total area of the face of the wire. When I add them all up, it gets me the total charge flowing through the wire. So I can either take the derivative with with the area to get J, or I can integrate J dA to get I. Now the surface current density, right, we define in an interesting way, and we're looking at 2 dimensions instead of 3. So the way I tend to think about this is, imagine I have a large flat plane conductor, and current is flowing in that conductor on the sheet of conductor, and I take a little strip, right? Di, the amount of current flowing in that little strip, divided by how thick that strip is, right? dl perpendicular. That will tell me what my surface current density is, right? So that is going to be defined as the surface charge density times the velocity. Cool?